Hello, everybody. Welcome back to Math Dmat 0315 and Math 1314. We are on day 19, beginning of the 10th week. Last week, we discussed the first part of chapter 4. The most important parts were the rational zeros, Descartes' rule of signs, and how to do synthetic division. All right. Given any size polynomial, and I'll just start something pretty small. Yes, we can factor this one out, but we'll try to use Descartes' rule of signs and the rational zero theorem to try to figure this out. So right now, if we were to trying to solve this, try to pick any values of x, try to solve this, we have an infinite number of possibilities. We start with 1, -1, 2, -2. Then we'll go to half. Then we'll go to 1/4, 1/8, 1/16. We can try any fraction, try to make this thing work. But that's where the rational zeros comes in, as well as the Descartes' rule of signs. First off, Descartes' rule says this. The number of sign changes in the original equation tells us the number of positive solutions possible. Then 2, change x to -x, and those sign changes tell us the number of possible negative solutions. So that narrows it down. It tells us how many positive negatives. The rational zero theorem, it will give us the possible positive, negative solutions and everything else that might work. Remember, there are only n solutions. Where n is the degree of the polynomial. The rational is p over q, plus or minus. All right, so let's look what we have here. Number of positive solutions possible. All right, so we do look for sign changes. Just look at the coefficients and the signs. This is positive, positive. That's not a sign change. Positive to negative, that's one sign change. So that means in our solutions, we're going to have one positive answer or solution. Remember, our solutions are x-intercepts. Now we have to change x to negative x in our equation. Okay, so if it has an even exponent, just drop the negative, and that doesn't change. If it's an odd exponent, this is x has a 1, so that's going to be a sign change. That's going to change the sign of the sign in front of it. Now repeat the process. Here's a positive to a negative. That's a sign change. Negative, negative, that's not a sign change. So we're going to have one negative solution. So we know we have one positive, when we're going to have two solutions. One of them is positive, one of them is negative. So now let's look at all our possibilities. That's P, that's Q. Sorry, that's Q over P. Q over P plus or minus. So Q is 15, P is 2. What we have to do here for the rational zeros is what are the factors, the combinations that make up 15? 1 times 15 3 times 5. And which makes up 2? 1 times 2. So now what we do is take each of these numerators on top of each of those denominators separately. So we have 1 over 1 plus or minus 15 over 1 plus or minus 3 over 1 plus or minus 5 over 1. So that's all of them. Now for the 2, plus or minus 1 over 2 plus or minus 15 over 2 plus or minus 3 over 2 and plus or minus 5 over 2. So let's see which one of these can simplify. Plus or minus will be 1. 15 over 1 is 15. Plus or minus 3 divided by 1 is 3. 5. 1/2. 15 over 2. 13, or 3 over 2. And 5 over 2. So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 and times 2, so one's going to be positive or negative. So there are 16 possible answers to be our solutions. So now what we have to do, we take each of these and do synthetic division on our equation. 2, 1, negative 15, negative 1, 2, 1, negative 15. And the beautiful thing is, since we have one positive and negative, once we find one of the answers, then we don't have to do those. If it's positive 1, we don't have to check any more positives. If it's negative 1, we don't have to check any more negatives. So it'll knock off the last half of our answers. Bring down the first term and multiply and add. 1 times 2 is 2. 2 plus 1 is 3. 1 times 3 is 3. And that's negative 12. So that's not right. Negative 1 times 2 is negative 2. Negative 1, 1, negative 14. So it's not it. Right, so we'll keep on going. The next one we have is 3 and negative 3. So it's 2, 1, negative 15. 2, 1, negative 15. 3 times 2 is 6. 6 plus 1 is 7. 3 times 7 is 21. 21 minus 15 is 6. That's not right. Remember, we're looking for a remainder. This answer here has to be 0. If that's a 0, then that's a solution. Negative 3 times 2 is negative 6. Negative 6 plus 1 is negative 5. Negative 3 times negative 5 is positive 15, 0. So we know x equals negative 3 is our solution. Which now if we set this equals 0, so x plus 3 is one of our factors. This is our solution. That's our factor. Now, once we get a remainder of 0, we don't have to go back to the original. We just look it down here. So this one's a constant. This is the x. So we have 2x minus 15 equals 0. If we start off with 3 terms, we only have 2 terms left. So now we solve this one. 2x equals 15. So move that over there. Divide by 2. X equals 7.5. So x equals, let's leave it as fractions, 15 over 2. That's our solution. But 2x minus 15 equals 0 is our factor. So 2x squared plus 1 minus 15 factors out to 2x minus 15 not 15, 5. That's 5. 2x minus 5, and then x plus 3. Those are my factors. So that's how it all works. That's what we did last time. All right. Today we're going to look at rational zeros. This is chapter 4.5. Rational equations, or rational polynomial equations. Now, rational means fraction. So, for example, if we had 2 over x plus 1 over x plus 1 equals 5 over x squared plus x. If that's our polynomial rational equation. First step, factor all of the denominators. numbers. Because set them equal to 0, that will find what x's you can't use. Because remember, we cannot have a 0 on the bottom. So once our first step is figure out what x's can we not use. So that one's already factored out as far as it can go. This one's as far as it can go. This one, okay, you have an exponent, so it's factored out. Well, they both have an x in common. So so our denominator is x plus 1. So set them equal to 0. We know that our answer cannot be 0, or x cannot equal -1. That's what this is trying to tell us. We cannot use x equals 0 or -1. These have the name, and I'll get that next. So once you do that, once you factor it out, figure out which ones you can't use, then we have fractions and equal signs. Let's get rid of the fractions. Remember the 5 steps? The LCD. The LCD is simply the factored form of the denominator. Then multiply the LCD to each term. So we have x plus 1 times 2 over x plus 1 times 1 over x plus 1 equals x plus 1 times 5 over x plus 1. Reduce, in other words, cancel. So the x here cancels. So we have 2 times x plus 1. In the next one, the x plus 1 cancels. So we have 1 times x, which is x. And then equals x and x plus 1 both cancel. We just have 5. Multiply to get rid of any parentheses. So 2x plus 2 plus x equals 5. And now solve. So whenever you get rid of parentheses, always combine like terms. 2x plus 1x is 3x plus 2 equals 5. Subtract 2. And then divide by 3. X equals 1. Before we say that's our solution, we have to come over here. Is it one of these two? We cannot use 0 or -1. So that's our solution. So it's the same thing we've been doing, but now we're doing with polynomials in the bottom. Now, whenever you have rational equations, you will have what are called asymptotes. Asymptotes are values that cannot be used in the equation that lead to lines that the graph cannot cross. That's what an asymptote is. An asymptote, it's a value or values that cannot be used in an equation that lead to the lines that of the graph that cannot be crossed. So those are asymptotes. So whenever you have rational equations, you'll have asymptotes, values that you can't use, and that which correspond to lines where that your graph cannot cross. Let's see what this means. Let's look at our example here. Our example here was 2 over x plus 1 over x plus 1 equals 5 over x squared plus x. First step was we factored out the denominators. And then we set the bottom equal to 0. And we solved it. These are two x values that we cannot use. These are called your vertical asymptotes. Because they're the x values. So in our graph, we cannot use 0. So we put a dotted line here. We can't use 0. And we can't use -1. So we have another dotted line we cannot cross. So vertical asymptotes are values that make the denominator equal to 0. Those are your vertical asymptotes. Those are the lines your graph cannot cross. We worked it all out. We set, now in our final solution, we set our x equals +1. Well, that's your x-intercept. That's a possible solution. Let's see, if we put 1 in there, will it equal 0? 2 over 1 is 2. 2 plus 1 half. 2 plus, let's see here. So we have 2 over 1 plus 1 over 1 plus 1 is 2 equals 1 times 2 is 2. So to get common denominator, which is 2, so we have to multiply this one top and bottom by 2. 2 times 2 is 4 over 2. 1 over 2 is 5 over 2. So 5 over 2 so equals 5 over 2. Okay, so it's not because if it was an x-intercept, then it would be equal 0. So this one's at 5 over 2, just 2.5. 2.5. So at 1, the point is there. So we know we have 1 point there. We can plug in some other values to see how the graph behaves. Let's try it. Let's see when x equals 2, what happens. And our equation is that one. So we have 2 over 2 plus 1 over 2 plus 1 is 3 equals 2 times 3 is 6. So multiply this one by 3, this one by 2. So we have 6 over 6. 2 over 6 equals 5 over 6. 8 over 6, 5 over 6. And that's not a solution because it's not equal. Which means now we have since they're not equal, it's not a solution. So what we have to do is now to figure out the graph here, move everything to one side, set it equal to 0. So we have 2 over x plus 1 over x plus 1. When we move this whole thing over, so we're subtracting 5x x plus 1. The equation has to be 0 to find an x-intercept. Now, before we do anything, we have to have a common denominator. So this one's missing an x plus 1. This one's missing an x. And then this one has them both already. So we have 2x plus 1, x plus 1, plus x plus 1, minus 5x plus 1 equals 0. Since we have a common denominator, x plus 1. So on top we have 2x plus 2 undistributed plus x minus 5. So 2x plus x is 3x. X plus positive 2 minus 5 is a negative 3. And leave the bottom factor. That's the equation for our graph. We have to have everything to one side. Now, our x-intercept, the only way fractions can be equal only set the numerator equal to 0. Right, so if I set the numerator equals 0, I've got 3x minus 3 equals 0, 3x equals 3, x equals 1. So at 1, okay, it was our x-intercept. So we have -1 is our asymptote, 0 is our asymptote, and 1 is our x-intercept. So the top, the numerator set equals 0 is our x-intercept. The denominator set equals 0 is our asymptotes. And because of that, we know that it's not going to cross the x-axis anymore, because if it did, it'd show us there. Okay, now there's another asymptote we can find. So we're still going to come back to this equation. We have a horizontal asymptote. The horizontal asymptote is determined this way. You only look at the leading terms of the numerator and the denominator, because the rest of the equation, it doesn't do that much. The leading term dictates the size, the graph, the shape, and everything. So in our equation, we have 3x on top and x squared on the bottom. So now we're going to tell you what the horizontal asymptote is. There are 3 conditions here. If the top value is bigger than the bottom, in other words, if there are more x's on top than there are on the bottom, no horizontal asymptote, because it goes to infinity. If the top and the bottom are the same, then the horizontal asymptote is simply the coefficients. And if the top is less than the bottom, then the horizontal asymptote is 0, or the x-axis. All right, so this is our horizontal asymptote, but we have a problem there. We can't have that. Well, we can't. There are situations where it will cross the asymptotes. So what we have to do is just plug in some values and see what the graph looks like. So we have 3x minus 3, x squared plus x, when it's 2 or -2. When x is -2. So we have 3 times -2 minus 3, -2 squared plus -2. -6 minus 3, 4 minus 2, so it's -9 over 2, which is -4.5. So -2 negative 4.5. Let's try negative 3. So we have negative 3, or 3 times negative 3 minus 3. Negative 3 squared plus negative 3. So negative 3 times 3 is negative 9 minus 3. Negative 3 squared is positive 9 minus 3. So it's negative 12 over 6, which is negative 2. So at negative 3, it's negative 2. So what we're seeing here is this is going to happen this way. All right, let's look what happens if we plug in 2, then 3. On the positive side, we plug in 2. So we have 3 times 2 minus 3. 2 squared plus 2. 6 minus 3. 4 plus 2. 3 over 6 is 1/2. So at 2, it's 1/2. How about 3? Oops. 3. So we have 3 times 3 minus 3. 3 squared plus 3. 3 times 3 is 9 minus 3. 9 plus 3, 6 over 12. Is 1/2. 3, so it's 9 minus 3 is 6. And that's 12. 6 over 12 is 1/2. How about 4? 3 times 4 minus 3. 4 squared plus 4. 12 minus 3, 16 plus 4, 9 over 20. So now it's going to go down. So it's going down. So this side looks like it's going like this. Now the question is, what happens in the middle? At negative 1/2. At negative 1/2. Let's do negative 1/3. Much easier. So we have 3 times negative 1/3 minus 3. Negative 1/3 squared plus negative 1/3. That cancels for negative 1. It's negative 4 on top. Negative 1 over 3 squared is 1 over 9 minus 3 over 9. So it's negative 2 over 9. So it equals negative 18. Because we have negative 4 on top and negative 2 over 9 on the bottom. Space. I'll put negative 1/3 there in place of x. Three's canceled, so we have on top negative 1 minus 3. Negative becomes positive, so it's 1 over 3 squared is 9 minus 1 over 3. Multiply 3 over 3. So we have 1 over 9 minus 3 over 9 makes it negative 2 over 9. So negative 4 over negative 2 over 9. This is a fraction, so it's negative 4 over 1. Take the bottom and flip it. 2 and the 4 cancel. So negative negative is positive 18. So at negative 1/3, it's 18. So it looks something like that. So that's what the graph's going to look like. So whenever you have rational equations, we're going to work a couple more of these. We'll get used to it. Whenever you have rational equations, factor both top and bottom. Whatever makes the bottom equal 0 are your vertical asymptotes. Whatever makes the top equal 0 are your x-intercepts. And then the horizontal asymptotes are dependent on the size of the x's. There's a couple more here. 2x plus 11. X squared plus 2x minus 8. No, not 11, let's make it 4. Make something easier here. First thing you do, factor top and bottom. What can factor out of the top? 2. Remember, when you factor out a number, to figure out what goes inside the parentheses, divide both of those by 2. 2 divided by 2 is an x. 4 divided by 2 is 2. Can we factor the bottom? X is x and x. Opposite signs. The bigger number gets positive. What times what is 8? When you subtract them, you get 2. 4 and 2. All right, so my vertical asymptotes. If you set these equal to 0, x equals negative 4, x equals 2. So my vertical asymptotes are negative 4 and 2. Those are the values my x cannot equal. My x-intercept is, here's x, it's at negative 2. Because the only place a fraction can equal 0 is if the top is equal to 0. And that's what we're looking for. How about the horizontal asymptote? So remember, we look at the leading terms. We have 2x over x squared. What's happening is this. We have 2x over x. This x cancels with one of those. We have 2 over x. Now, as x goes to infinity, where does this equation, the value, go? So listen, as x gets bigger, what happens? As the bottom number gets bigger, goes from 2 to 1/2, the number gets smaller, smaller, smaller. Eventually, it's going to go to 0. So when you have any number over x, it eventually goes to 0. So that's how come our second condition, our third condition. If the bottom exponent is bigger than the top, if the bottom exponent is bigger than the top, your value goes to 0. Your horizontal asymptote is 0. If the x's cancel out, then all you're left with are the coefficients. So in our example here, the horizontal asymptote is 0, which is the x-axis. So if we look at our graph, we cannot use -4, and we cannot use 2. Those are my vertical asymptotes. And the horizontal asymptote is the x-axis. That's y equals 0. And then we would take this equation, either one of these, and plot some points and see how they behave, where they plot. All right, so let's see where they plot. So I have 2x plus 2, x plus 4, x minus 2. And this is what y equals. So let's try 0. Let's see what happens when it's x is 0. 0 plus 2 is 2. 2 times 2 is 4. 0 plus 4. 4 times -2 is -8. It's -1/2. So at 0, it's -1/2. When it's +1, 1 plus 2 is 3. 3 times 2 is 6. 1 plus 4 is 5. 1 minus 4 is -1. So it's -5. When it's -1. -1 plus 2 is 1. So it's 2 on top. 3 times -3 is -9. So 2 over -9. Let's try -2 and -3. Remember, we cannot use x cannot equal -4 and 2. So plug in -2. That gives us 0 on top. So it's 0. -3. So we have 2 times -3 plus 2 is -1. So that's -2 on top. -3 plus 4 is -1. Times -5 is 5. So it's -2 over 5. So you notice all of these are negatives except for 2. -2. So at -2, it's 0. And everything else goes down. So on the bottom, it looks like this, in the middle part. Let's look at 3, 4, and 5. And then we'll do -5, -6, -7. 3, 4, 5. So 3. 3 plus 2 is 5 times 2 is 10. 3 plus 4 is 7 times 1 is 7. 10 over 7. It's positive. And it's 4. 4 plus 2 is 6. 6 times 2 is 12. 4 plus 4 is 8. 4 minus 2 is 2. It's 12 over 16, which is 6 over 8, which is 3 over 4. Let's look at 5. 5 plus 2 is 7 times 2 is 14. 5 plus 4 is 9. 5 minus 2 is 3. So it's 14 over 27. Yeah, so what's happening here is as x gets bigger, these are getting smaller. So it looks something like this. But if we use 2.5 or 2.1, it would be a pretty large number. Let's look at the negative side. -3. No, -5, -6, and -7. Again, we're using this equation. So -5 plus 2 is -3. -3 times 2 is -6. -5 plus 4 is -1. -5 minus 2 is -7. There are 3 negatives. It's -6 over 7. Negative. -6. -6 plus 2 is -4. That makes it -8. -6 plus 4 is -2. -6 minus 2 is -8. It's -1/2 because the 8's cancel. And -7. -7 minus plus 2 is -5. Is -10. -7 plus 4 is -3. -9. And -10 over 27. Okay. Actually, let me check on this side. Because this side looks like it's like this. These are all negative. These are all positive. I'm wondering if it's going to go up there. So let me try it. I try -3. I did that one wrong. Because if it was -3, be 2. -3 plus 2 is -1. -3 plus 4 is 1. -3 minus 2 is -5. The negatives cancel, so it's positive 2/5. It's positive 2/5. Yes. Since 2's, and so it'll go like this. That's what it's going to look like. Because yeah, these take a lot of time because you have to plug in a lot of numbers and just keep on trudging through. Right. I mean the vertical, the horizontal asymptotes of this equation. So again, what can we factor out of the top? We both have an x, so it becomes an x minus 4. What we both have on the bottom is an x, so we have an x squared minus 1. Okay, now even though I cancel those out, this x equals 0 is still one of my asymptotes, my vertical asymptotes. So whatever makes the bottom equal 0, if x is 0, it'll make the bottom 0, even though they cancel out. What this is called is a hole, because since it's the same on top and bottom, it's going to be a hole, but it's still an asymptote. Now, what else? This is a difference of two squares, x plus 1, x minus 1. Set both of these equal to 0, so my vertical asymptotes are -1, +1, and 0. Now, since there are more x's on the bottom than the top, my horizontal asymptote is the x-axis, because there are more x's on the bottom. Same thing, horizontal and vertical asymptote. And horizontal asymptote, vertical asymptote, and x-intercept. Let's go one step further this time. First thing we have to do, the top is already factored out. The bottom, they both have an x, so I have x squared minus 4. It's a difference of two squares, so it's x squared minus 2 squared. Remember, whenever you have a square with a minus after it, see if the second that number back here is a perfect square. So it's x squared minus 2 squared, so it's x plus 2, x minus 2. The vertical asymptotes are at 0, -2, +2. Even those cancel out. That's going to be a hole at the x at this one here, but it's still an asymptote. Since we have more x's on the bottom, the horizontal asymptote is 0. Set the top equal to 0. The x-intercept is 2. But the 2 cancels out. That's why it's going to be a hole there. And then we would graph that. Let's look at another one. Negative 2x squared minus x plus 15, x squared minus x minus 12. Tell me the x-intercept, the y-intercept, and the zeros. I mean the x-intercept, the vertical asymptote, and the horizontal asymptote. So the first thing we have to do is factor these two equations out. On the top, since your leading term is negative, you have to factor out a negative. So change everybody's sign. And the bottom, leave it alone. Let's factor the bottom. So we have x and x. There's a negative sign there, so they're both opposite signs. The bigger number will have a negative. What times what is 12? When you subtract them, you get 1. 4 times 3. And 4 minus 3 is 1, so that works. Now, let's do the top. Since that's not 1, so we put 2x and 2x. Negative, so signs are opposite signs. The bigger number will have a plus. So figure out what times what is 15. When you subtract them, equal 1. Nothing, because 15 times 1 is 3 times 5. Nothing equals 1. So what we have to do then, so we can't factor them. So the numerator is a little too hard to factor. Okay, so we know our vertical asymptotes are at -3 and +4. See, opposite signs. The horizontal asymptote, since the leading term, x's are the same, you just take the coefficients. -2/1 is -2. That's the horizontal line at y equals -2. So at -2, there's a horizontal asymptote there. At -3 and at 4, there are vertical asymptotes. So the only way we can find the x-intercept for this equation is by quadratic formula. A is -2, B is -1, C is +15. We can check to see if the discriminant is going to be positive, negative, or 0. -1 squared, 4 times -2 times 15. So +1, 8 times 15. It's 120. So it's 121. So -b plus or minus b squared 4ac over 2a. Negative over -1 plus or minus, we did this already, so it's 121 over 2 times a -2. So that becomes positive. So we have 1 plus or minus square root 121 is 11 over negative 4. 1 plus 11 is 12 over negative 4 is negative 3. 1 minus 11 is negative 10 over negative 4 is 4 over 10 or 5 over 2. These are my x-intercepts. But since my vertical asymptote is negative 3, I can't use it. So the only x-intercept I have is at 5 over 2 or 2.5. That was a more complex one. One more. And then we'll talk about another type of asymptote. So it's x-intercept, the vertical asymptote, and the horizontal asymptote. So the first thing we have to do is, if possible, let's factor. So on the bottom is opposite signs. What times what is 2 when you subtract and you get 1? 2 times 1. 2 minus 1 is 1. So the negative goes on the 2. So the vertical asymptotes are at negative 1 and positive 2. My x, but these guys cancel. So my x-intercept would be at 2, but it's a hole, so it's not really an x-intercept because they cancel. Now, since the leading terms for the horizontal asymptote, leading terms, it's x over x squared. Because there's more on the bottom than the top, we would say there isn't one, or it's 0. But here's an exception. No, this still would be 0 because the bottom is bigger than the top. The only exception we have is this. For the horizontal asymptote, since the top is bigger than the bottom, we would say that there's none. Because as x gets bigger, there's more of my top, it goes to infinity. But except when the top exponent is bigger than the bottom exponent by 1, then we have an oblique or slant asymptote. So if the top exponent is bigger than the bottom by 1, then we have an oblique asymptote. Do long division, and the equation of the line that comes out is your oblique asymptote. Okay, well, so we could try this one. So what we have to do now, anywhere where you have a number missing, an exponent missing, you have to put a 0 in its place. We have x cubed. There's no x squared, so we put a 0 x squared. There's positive 4x, and then there's no constant at 0. So we have to have all the columns allocated. What times x squared gives me x cubed? Remember that when we do long division, always look at leading terms. What times x squared gives me x cubed? X. So x times x squared is x cubed. X times 2x gives me 2x squared. X times 1 gives me x. Change the signs and add. Remember, the leading term has to cancel. 0 minus 2 is minus 2x squared. 4 minus 1 is 3x. Bring it down to 0. What times x squared gives me negative 2x squared? Negative 2. So negative 2 times x squared is negative 2x squared. Negative 2 times 2 is negative 4x. Negative 2 times 1 is negative 2. Change the signs. 4 plus 3 is 7x plus 2. Now, since I can't go any further, this is my oblique asymptote. My oblique asymptote is the equation y equals x minus 2. Remember how we graph those? Plot the y-intercept first at negative 2 and follow the slope, up 1, over 1. There's your slant asymptote. All right. And so the vertical asymptotes, we set the bottom equals 0, we factor those out, we get x plus 1, x plus 1. So we'd have a vertical asymptote there. So our graph would look something like this. It's either going to be inside this one or inside those. It's always got to be opposite each other. So let me summarize the rules for asymptotes. One, vertical asymptotes. Of course, this is after you get all of the equations factored. Vertical asymptotes. Set the denominator equal to 0. The x values are your vertical asymptotes. The horizontal asymptotes. Remember what you're going to have you're going to have some equation. You only look at the leading terms. And to determine the horizontal asymptotes, you look at the exponents of the variables. If the top exponent is bigger than the bottom exponent, it means there's more x's on top, then your horizontal asymptote does not exist. None. In other words, if there's more x's on top than the bottom, then it goes to infinity. If the top and the bottom both have the same number of exponents, then your horizontal asymptote is simply the coefficients, a over b, because the x's cancel. And if the top is smaller than the bottom, your horizontal asymptote is 0, or the x-axis. Because the horizontal asymptote is the equation y equals 0, y equals a over b. And the vertical asymptotes are your x values. That's why they go up and down, and these go left and right. All right, but there's an exception. You have an oblique asymptote. If the exponent on top is exactly one number bigger than the exponent on the bottom, then do long division. Do long division twice, 2 times, because you can get rid of the x's and then get your constant. Whatever linear equation you end up with is your oblique asymptote. All right, so that's what we have. That's section 5. Let's look at section 6, inequalities. polynomial and rational inequalities. Let me get some example points here. All right. We're doing polynomials first. Polynomial inequalities. First step, move everything to one side. Zero on the other. So you have to have zero to be able to compare it. The reason being, for inequalities, we can only determine whether it's greater than or less than. We can't say really if it's equal to. It doesn't do us any good. So move everything to one side. Factor to find the x-intercepts. Because what you're going to do is graph it. Plot the y-intercept. Determine the shape and direction then you'll evaluate it. Choose a point not on the graph. Plug it in. If the statement is true, then shade that side of the graph. If it's false, then shade the other side. And you're done. So that's all we're doing here with inequalities is we're shading one side or the other. So those are the steps. So let's look at this. So we have a polynomial. We know it's quadratic, so it's a parabola. It opens up because a is positive. Let's go ahead and graph it. We have x and x. Both sides are the same. They're both positive. What times what is 8? When you add them, you get 6. 4 and 2. So x equals -4 and x equals -2 are my x-intercepts. The y-intercept is at 8, and it opens up. So we have -2 and -4. Those are my x-intercepts. 1, 2, 3, 4, 5, 6, 7, 8. Find my vertex, negative b over 2a, and plug it in there. So a is 1, b is 6, c is 8. So negative 6 over 2 times 1 is 2. Makes it negative 3. That's my axis of symmetry. Because remember, the x value of my vertex is my axis of symmetry. So it means if I go 1, 2, 3 to the right, I go up, I got a spot. So if I go 1, 2, 3 to the left, and I go up 8, I got another dot. Because I get one dot both sides. And I keep on going to the other one. So now I plug in negative 3 to the equation. Negative 3 plus 4 is 1. Negative 3 plus 2 is negative 1. So 1 times negative 1 is negative 1. There's the graph. Now, this is important about the graphs. If it's a greater than or less than equal to, your graph will be a solid line. If it's like this, your graph will be a dotted line. So it's like this or like this. But since our equation is less than equal to, we have a solid graph. So that's what we did. We graphed our thingy. Now let's choose a point that's not on this graph itself. If you can use 0, use 0. Because remember, our equation, we're saying it's less than 0. So when x is 0, that's gone. Is 8 less than equal to 0? No, that's false. So I can't use that point. That means I could use anything inside here. That's how you do it. So you pick a point that's an x value that's not on the graph and plug it in there. And since we're saying that our x values are below, less than or equal to 0, the only place that's going to be true is if here. So if I plug in negative 3 inside there, negative 3 plus 4 is 1. Negative 3 plus 2 is negative 1. 1 times negative 1 is negative 1. That's less than 0, so it works. So all my values that I can use are inside there. Let's do that. X squared plus 7 is greater than 8x. All right, so the first thing I have to do, I have to put everything one side, which has to be 0. So I have to subtract 8x from both sides. x squared minus 8x plus 7 is greater than 0. Factor it out, because we need to graph this line. It's a parabola, so we know, and this is positive, so we know it's going to take that. X and x, they're both the same signs. They're both minus. What times what is 7? When you add them, you get 8. 7 times 1. Solve both of those, so I get x equals 7 and x equals 1. And my y-intercept is at 7. Nine. 1. 1, 2, 3, 4, 5, 6, 7. So there's my y-intercept. And I have an x-intercept at 1 and at 7. Where's my vertex? A is 1, B is negative 8, C is 7. So the x value is negative b over 2a. Negative of a negative 8, 2 times 1. 8 divided by 2 is 4. So 4 is my axis of symmetry. So I know 1, 2, 3, 4, up 7. 1, 2, 3, 4, up 7. Another dot there. Right, let's see where the y value is. I take this point, plug it back, or I can plug it into here, it's easier. 4 minus 7 is negative 3. 4 minus 1 is 3. So 3 times negative 3 is negative 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, my graph will be on this plot. But since it's strictly, there's no line underneath it, my graph will be a dotted line. That distinguishes whether it's less than equal to or greater than equal to or not. Okay. Now we have to pick whether the graph is outside this or if it's inside that. So I pick a point right there. If I can use 0, 0, I'm going to use 0, 0. Because my x value is 0, I plug it inside the equation. 0 squared root of 0 minus 0 is 7. Is 7 greater than 0? Yes, that's true. So 7 is greater than 0. True. Since that means these are my solution points. Right, that's how you do that. All right, we do the same thing with rational equations. Get one from the chapter. So we have x plus 1 over 2x minus 4 is less than equal to 1. So x plus 1 over 2x minus 4 steps. make equal to 0. So notice I move everything over. So I have x plus 1 over 2x minus 4. I subtract 1 from both sides. Now I got to fix this first. So this is 1 over 1. I need to have a 2x minus 4. So it's 2x minus 4 over 2x minus 4. So my common denominator is 2x minus 4. Here I have x plus 1 minus 1 times 2x minus 4 is less than equal to 0. I can drop the first parenthesis. The negative switches over, distributes. Negative times positive is negative. 1 times 2 is 2x. Negative and negative is a positive. 1 times 4 is 4. Combine my terms. Negative 2x plus 1x is negative x. 4 plus 1 is 5. All right. So we have a rational equation. First, the x-intercept. Set the top equal to 0 and solve it. So I'm going to add x to both sides. X equals to 5. So my x-intercept is at 5. My vertical asymptote. Set the bottom equal to 0. 2x equals 4 divided by 2, x equals 2. So that's my vertical asymptote, is at 2. So at 2, I cannot use. And at 5, that's my 0. What I'm looking for here I'm looking for the x values that make it true. So what I'm looking at here are, I'm looking at this interval. I'm looking at these intervals from negative infinity to 2. I'm looking from 2 to 5. And then from 5 to infinity. What's going to happen in all of these? I want it to be less than equal to 0. So let's try a value at 0. If we put 0, if this one works, then all of these x values work. So we have 0 plus 5 is 5. 0 minus 4 is negative 4. So it's negative 5 over 4. Is that less than 0? Yes. So we can use, so zeros will work. So this part will work. How about between here? Can we use 3? Negative 3 plus 5 is negative, or 2. 3 times 2 is 6, minus 4 is 2, is 1. Is 1 less than 0? No, so I can't use that. Let's try 10. Negative 10 plus 5 is negative 5. 10 times 2 is 20, minus 4 is 16. That's negative. So I can use this. So my solutions are from these two sets. So what we're looking for the x values that are possible that make it work. Okay, let's go back to this one. So when we factor this one out, we had x plus 4, x plus 2. We set these equal to 0. We got negative 4 and negative 2. So we're looking for the intervals. I'm sorry, when I did the other one, I was graphing them. We're not ready for that yet. I jumped way too far for that. So we take our polynomial, factor them out. It has to be 0 on one side. And these two values are called our critical values. We're looking at this interval. We're looking in there. We're looking at this interval. And we're looking at this interval. We're trying to see which x values can we use and still keep this a true statement. So let's say we pick negative 10. Negative 10 plus 4 is negative 6. Negative 10 plus 2 is negative 8. Negative is positive. That's not less than 0. So that's false. Now between negative 4 and negative 2 is negative 3. So negative 3 plus 4 is 1. Negative 3 plus 2 is negative 1. Is negative 1 less than 0? True. So we can use this area. We can't use that. We can use this one. And likewise here, let's pick 0. 0 plus 4 is 4. 0 plus 2 is 2. Is 8 less than 0? No. So the only ones we can choose is this interval. That's our solution. All right. The same we just did. Has to be set equal to 0. So we have to move the 8x over by subtracting 8x. Factor it out. So we have x and x. The same sign, they're both minus. 7 times 1 is 7. 7 plus 1 is 8. So we see our answers are at 7 and 1. So what interval can we use? Can we use negative infinity to positive 1? Remember, it's not equal to, so it's parentheses. Can we use 1 to 7? Or can we use 7 to positive infinity? Let's pick a value. Negative 2, or let's say negative 1. There's anywhere between here. Negative 1 minus 7 is negative 8. Negative 1 minus 2 is negative 2. Negative negative is a positive. Positive 16. Is 16 greater than 0? Yes. So we can use this. How about between 1 and 7? Let's pick 5. So 5 minus 7 is -2. 5 minus 1 is 4. Negative to positive is negative. 2 times 4 is -8 bigger than 0? No. So we can't use that interval. Now, between 7 and let's pick 10. 10 minus 7 is 3. 10 minus 1 is 9. 9 times 3 is 27. Is 27 greater than 0? Yes. So our answers are in this interval. So basically, whether if it's an open, if it's doesn't have a line, then they're open circles. You know, I went a little bit too deep with y'all for this. Sorry. So with the polynomials inequalities, that's how you do it. Let's just do another one. Let's look at this. We have a 0 on one side. Check. Let's factor this one out. They all have an x, so we'll take out an x. This is a difference of 2 squares. It's x squared minus 3 squared, which means x plus 3, x minus 3. So these are called my critical values. They are x equals 0, -3, +3. -3, 0, +3. Since these are equals, they're solid dots. So I have to check to see which intervals work. I'm going to use this one, it's much easier. So I'm going to pick -5. So -5. -5 plus 3 is -2. -5 minus 3 is -8. I'm looking for greater than 0 means, is the answer going to be positive? Negative times negative, negative, this is going to be negative, so that fails. Because it has to be positive, it has to be greater than 0. Between -3 and 0, let's try -1. So we have -1. -1 plus 3 is 2. -1 minus 3 is -4. Negative, negative is a positive, so this works. Between 0 and 3, let's try 1. So we have 1. 1 plus 3 is 4. 1 minus 3 is -2. Positive, positive, negative is negative. It's not greater than 0, so that fails. So I can't use that. And let's try 10. So we have 10. 10 plus 3 is 13. 10 minus 3 is 7. They're all positive. That's greater than 0, so that works. So my answers are in these domains. So yeah, so all you're looking for here are the x. The reason being is because if you look at our original equation, there's no y, so there's no graph to it. So all we're looking for are x values that make this a true statement. All right, so you have to get it equal to 0 on one side, factor it out, find the critical values, and then see which one works by pick a number between negative infinity and negative 3. Pick a number between 3 and 0. Pick a number between 0 and 3. You have to try each one of those, and the ones that satisfy the condition on top, or if I'm looking for a number that's greater than 0, what will make this greater than 0? What will make this positive? I'm only looking for positive answers. So these are the ones that work. The same thing with the rational equations. The exact same ones with the rational equations. X over x squared minus 4 is less than 2. Let's say 2 over x plus 2. So we have to make it 0 on one side. So let's subtract this whole equation from both sides. So we have our original equation minus what we just put over here. 2 over x plus 2 minus 2 over x plus 2, those cancel, so we get a 0 there. That should be 2, not 4. So factor the bottom. This is already factored. This one is x squared minus 4, which is x squared minus 2 squared, which can be factored out as x plus 2, x minus 2. It's a special case, a difference of 2 squares. So the first one is x plus 2, x minus 2, and the second one is 2, x plus 2. It's less than 0. So to get a common denominator, they both have an x plus 2. This one needs an x minus 2. So put it top and bottom. So they both have an x plus 2, x minus 2 on the bottom. And on top, we have this. So we got to fix the top. Negative 2 times x, negative 2x. Negative times positive, negative times negative is positive. 2 times 2 is 4. X plus 2, x minus 2 is less than 0. Put that next page. So we have x minus 2x plus 4, x plus 2, x minus 2 less than 0. 1x minus 2x is minus x. Okay, now, remember, we want to be strictly less than 0, so it cannot equal 0. So let's see on the top. Negative x plus 4. What would make it equal to 0? So if we add x to both sides, x equals 4. So x equals 4 is one of the points we have to take in consideration because it has to be less than 0. And then the other two are negative 2 and positive 2. So my critical values are negative 2 positive 2, and 4. These are the values I cannot use. I cannot use this one because if I use 4, it equals 0, and that's not enough. I'm looking for less than 0. So let's see what we have here. Let's pick a number between negative infinity and negative 2. Let's try negative 10. We want it to be less than 0. So we're looking for only numbers that are negative. So we plug in negative 10. So negative, negative makes it positive. 10 plus 4 is 14. Negative 10 plus 2 is negative 8. Negative 10 minus 2 is negative 12. Negative, negative is positive. This is going to be a positive. So I can't use any of those numbers. Between negative 2 and 2, let's use 0. So 0 plus 4 is 4. 0 plus 2 is 2. 0 minus 2 is negative 2. So it's a negative 4 on the bottom. So, so I can use this area. So I can use between negative 2 and 2. How about between 2 and 4? 3. Negative 3 plus 4 is 1. 3 plus 2 is 5. 3 minus 2 is 1. So it's all positive. I'm looking for less than, so I can't use anything there. How about after 4? How about 10? Negative 10 plus 4 is negative 6. 10 plus 2 is 12. 10 minus 2 is 8. So it's going to be negative. So I can use these values. So these are my answers. So what you have to do is when you have a rational equation, get 0 on one side. Simplify the other side. Factor it. Set the numerator equal to 0. Set the denominator equal to 0. Because we have 0 on one side. If it equals 0, then we can use that number. If it's not, then we cannot use that number. Cannot use that number. And we cannot use these. So we cannot use these. So those are our critical values. Denominator 1, denominator 2, and numerator. If like this, solid dots, then open. So these are going to be brackets, these are going to be parentheses. And that's how you do it. All right, I hope that helped. That does it for that chapter, I believe. Let me see. Chapter 4. One, two, three, four. Polynomial. Yeah, that does it. So we're finished chapter 4. What we'll do in class on Wednesday is we'll go over all the questions anybody has. And then next week we'll start chapters 5, 6, 7, and however far we'll go. All right. Good luck, everybody. And I hope nobody's stuck in the rain because it's pouring down here. So, all right. Have a great day, everybody. I'll see y'all Wednesday.